Hi guys, welcome to my YouTube channel. Today I'm going to help students in how to answer paper 3. This is advanced practical skills. Basically this video may not help students, it will help mostly teachers, but maybe students will find it useful. I'll record two questions for number 2 and two questions for number 1, and I'll be using results for my students. So this is advanced practical skills. This is supposed to be paper 3, and recently my students did this practical, and I asked one of my students for their results so that I could use it to record this video. So I'm going just to use the results of my students to record this video so that students can find it helpful when they are doing their practical. So for the teachers, you may use this video. You just print the paper and pick the apparatus, give to your students. Then maybe you may use my results as a guiding tool. You may use my results as a marking tool for your students. So without wasting time, in this video, I'm recording only question number 2 because I have results for question number 2. So let's go to number 2. Number 2 is the most complex question to many students. Although it is the easiest, it is the shortest. So question number 2, this is how the question was looking like. In this experiment, you will investigate how the motion of a meter ruler balanced on a cylinder depends on the diameter of the cylinder. In case you're a student, you can ask your teacher to give you the apparatus, and maybe you do the experiment, get results, and compare with mine. This video is just to help you to learn how to lay out your results and how to write the results. So I'll just show you how my student wrote their results. So because they were measuring the thickness of a meter ruler which is not uniform, the examiner will be looking for repeated measurements. So for repeated measurements, I drew a table because I'm going to take the measurement at least twice. You don't need to draw so many columns. You just need to show evidence of repeated measurements. So you draw a very neat table for your results because you are going to repeat the measurement. So my student took the first measurement for thickness. You were provided with a vernier caliper. I provided my students with the digital vernier calipers which measure in millimeters and 2 decimal places. So you may be having a manual vernier caliper which measures in centimeters to 1 decimal place or to 2 decimal places, but this was digital measuring in millimeters to 1 to 2 decimal places. So the units here are going to be millimeters. So the student did the second attempt also in millimeters. The first measurement the student obtained was 7.2 millimeters. 7.27 millimeters and 7.33 millimeters. These were the results for this student. So at this point here, we need the average. So the average thickness is of course 7.27 plus 7.33 divided by 2. So the average thickness was 7.27 plus 7.33 divided by 2. So this student wrote their average as 7.30. To maintain the same degree of accuracy, this student got 7.30 in millimeters. He added a 0 so that the precision of the instrument is maintained to 2 decimal places. So this would give this student a mark. Now remember, the mark is not for the answer, the mark is for the method, and the method here is taking a repeated measurement because the thickness of the meter ruler may not be uniform, so you take a measurement at different points. Like I said, you don't need to draw a very large table with many columns because even if you do many columns, the examiner is just looking for the fact that the student knows that they need to take another measurement, or they need to repeat the measurement at different points and obtain the average. So this will be the results for my student. Then part measure the diameter, measure and record the diameter D of cylinder A. They were provided with 2 cylinders. You can, your teacher can check in the confidential and see which cylinders are provided. So because even the diameter of the cylinder could not be uniform, the student took another repeated measurements. So for repeated measurements, the student draws a table. Okay, so the first attempt, the student used the same instrument, which is a digital vernier caliper, to measure the diameter. The cylinder could be large, so you could use a meter, a ruler, you could use an analog vernier caliper, but this student used a vernier caliper which measures in millimeters. To do the small places, it was digital. So these are the values she obtained. So D1, the first attempt in millimeters, second attempt in millimeters for the same cylinder. For the first attempt, she had 52.70. For the second attempt, she had 52.35. You could use different cylinders. So these values in the table could be changed. They could be different. So then we're interested in the average. So the average diameter is going to be 52.70 plus 52.53, and this is divided by 2. So we can check the student's average. 52.7 plus 52.23 divided by 2 to find the average. Sorry, 52.7 plus 52.23 divided by 2. So this student had 52.46. Sorry, this is 35, not 5. This is 35. So 52.7 plus 52.35 divided by 2. So this is 52.525. So to maintain the same precision of the instrument, this student writes 52.53. This was 52.525. So the student writes 52.53 to maintain the same precision of the instrument. So this is in millimeters. So this would give the student a mark. Then calculate W, where W is D minus T. So this was easy. For subtraction, we shall maintain the number of decimal places. So W is going to be equal to D, which is 52.53 minus 7.30. So 52.53 minus 7.30, and this student got 45.23. So this is 45.23 in the same unit millimeters. So the student gets that mark. Then use modeling clay to secure cylinder A to the bench and balance the meter rule on the cylinder. You can follow the instructions if you have a printed copy. So this was how the ruler was to be balanced. Then move one end of the rule downwards, release the rule and watch the movement. The end of the rule will move upwards and downwards again, completing a swing as shown. So there were timing oscillations here. There were timing oscillations. The time taken for each complete swing is T. So you couldn't time one oscillation. So my students chose to time 10 oscillations. Others chose to time 5 oscillations. So for this particular student I'm considering, whose results I'm using, she timed 5 oscillations. So if you are timing 5 oscillations, then you draw a table, because you may do the attempt twice. So you draw a table of results, a very nice table. Okay, so she timed 5 oscillations, but she did it twice. So she timed the first attempt 5t in seconds. She repeated again for the same 5 oscillations. Then she obtained the average and again divided by 5 to get time for one oscillation, because they told us that t is the time taken for a complete swing. So for the first attempt, time for 5 oscillations was 17.59. When you do the practical, you may not get the same value. For the second attempt, time for 5 oscillations was 21.06. Of course, there is a large difference, but this is measuring time. Reaction time is not always the same. So then, first of all, she first found the average. The average of 5t is just these two divided by 2. So she got 17.59 plus 21.06 divided by 2. This is the average for 10. But remember, we want time for 5 for one oscillation. So she divided again both sides by 5. So this will be times 5 so that we get for one oscillation. So we have 17.59 plus 21.06. So I'll divide this by 10 in the denominator. And she got 3.865. This is 3.865 in seconds. So that's what she got. So she tried to maintain the same number of significant figures, 1, 2, 3, 4. So she recorded here her value as 3.865 seconds to 4 significant figures, just like the raw data is provided to 4 significant figures. Okay, so this is what she obtained here. Of course, timing 5 oscillations would give her a mark, and of course recording the average would give her the second mark. You could also have timed 10 oscillations. You can check with the 10 oscillations. If you check 10 oscillations and you repeat, then in the table you would write 10t in seconds. You repeat 10t in seconds. You obtain the values. Then find the time for one oscillation. You would say 10t is equal to the first attempt plus the second attempt. Then divide by 2. But remember, if you want for one oscillation, you will say times 10. Here you divide by 10 so that 10 cancels out. So the first attempt you get plus the second attempt divided by 2 times 10. So this would give you a value for time in seconds, for the time for one oscillation in seconds. You can try with the 10 oscillations if you notice that they can reach. So in red is just a contrast. It is just another way of doing it if you want to time 10 oscillations. Okay. Then the most important part, the most important reason as to why I've recorded this is this part here. Starting with this part, estimate the percentage uncertainty in your value of t. Percentage uncertainty in your value of t. I'll do two methods. Since it is time, I'm going to divide this space into 2 so that I do 2 methods. You choose one. For time, I know that the reaction time of a normal human being is 0.2 seconds. That is the normal reaction time. But then when you look at the stopwatch used, it measures the least count is 0.01 seconds. That is the stopwatch used. But the reaction time is 0.2. Remember, you are pressing start, you are pressing stop. So total reaction time could be approximately 0.4. That means the absolute uncertainty in this, the absolute uncertainty, you could say the absolute uncertainty is equal to, now for the absolute uncertainty for a stopwatch, you can choose a value between 0.2 up to around 0.5 seconds. Because of reaction time, starting and pressing the stopwatch, I can choose the absolute uncertainty in that range. So I'll choose in that range and I'll say, okay, it is 0.3 seconds as my absolute uncertainty. So if I want the percentage in t, percentage uncertainty in t will simply be 0.3. That is the absolute divided by the true value of t, which is 3.865. Then I multiply this by 100. So I get the percentage uncertainty in that case, 0.3 divided by 3.865 times 100. So this would give me 7.8%. So the percentage uncertainty in this case will be 7.8%. That would be my percentage uncertainty here. Another method would be I could choose because I have different values of time, I could choose the absolute uncertainty as half of the range. So this was method 1. Method 2, I will use a different color. If whenever you have repeated measurements that are different, you can choose the absolute uncertainty to be half of the range. So absolute uncertainty is equal to half of the range. Half of the range. So this is going to be equal to half of the range, so that will be a half. The range is going to be, since I have different values, it's going to be 21.06 minus 17.59. That is going to be my absolute uncertainty. The difference between those two values divided by 2, that is half of the range. So 21.06 minus 17.59. So that is going to be divided by 2. So this is giving me 1.735. So this is 1.735. This is going to be the absolute uncertainty. Of course, it is in seconds. This is the absolute uncertainty in seconds. So if I want the percentage uncertainty in T, this will be 1.735 divided by 3.865 times 100. This will be percentage. So this is going to be that divided by 3.865 times 100. So that is going to be 44.9%. 44.9%. So this value, of course, is big, but of course, like I said, the examiner will not mark the answer. The examiner is interested in the method. So either this one or this one, they will both be acceptable, even though this is large. Of course, what makes this large is because of this large difference in the values of time, but that's fine. So I'll write here one of the answers. I'll just write here one of them. You can choose which one to take. Remember, it is just the method, not the answer. So the answer here, I would write here 7.8%. Or you can write there 44.9%. Don't ask me that the answers are different. I say the examiner marks the method, not the answer. In the first part, the method is suggesting an acceptable absolute uncertainty. In the second part, the method is knowing that the absolute uncertainty is half of the range. That's where the 1 marker goes. So the preceding working will not be very important, although you have to do it and complete to write the percentage. So that is fine. Then next, repeat the procedure. Repeat B and C for cylinder B. So they had another cylinder which was larger, I think. So again, they repeated the measurement. They measured the diameter, of course, taking repeated measurement, drew a table. So my student drew a neat table. I will also draw a table here for D. So is measuring diameter for the larger cylinder. So D, again it did D1 in millimeters, D2 in millimeters. So for the first attempt, she measured the one part and it was 118.88. Then for the second attempt, it was 119.24 using a digital vernier caliper, and obtaining the average diameter. The average diameter was 118.88 plus 119.24 divided by 2. So 118.88 plus 119.24 divided by 2. So she got 119.06 millimeters. So that is the diameter, 119.06 millimeters. Then W, remember W was just subtracting. What was W? How did we find W in the first part? In the first part, W was D minus T, where T was the thickness of the roller. So we just subtract. We find W. W is D minus T. So D is 119.06 minus T, where T was the thickness of, small t was the thickness of the roller, which is 7.30. So we subtract 7.30. 7.30. Okay, so minus 7.30. So that is 111.76. 111.76 in millimeters. So that is W. Then for T, my student again repeated. This time she timed 10 oscillations. So if you time 10 oscillations, draw a table, find a period, time for one cycle. This time we are using a bigger cylinder. Okay, so this time she tried 10 oscillations, so 10t in seconds, first attempt. She repeated again 10t, second attempt. So the first attempt she got 25.81. The second attempt she got 26.34. So she found time for one oscillation. First of all, 10t, the average for 10t would be 25.81 plus 26.34, then divide by 2. But because I want one oscillation, I divide by 10. So I divide by 10 the other side also, so that I have time for one cycle. So this is simply going to be 25.81 plus 26.34 divided by 20, which gives us 2.6075 in seconds. So to maintain the same accuracy, I'll just take 4 significant figures. So this will be 2.608 seconds. So that will be the value for T. Now this one will give my student 4 marks. I'm very certain. Taking a repeated measurement for D, that will give you the 2 marks. Taking repeated measurements for T would give the student another mark. Of course, subtracting will not give any other mark. Okay. Then next, it is suggested that the quantities T and W are related by the equation T squared is equal to K over W. Using your data, calculate two K values. So my student makes K the subject, K is equal to T squared times W, and she goes ahead to calculate two K values. The first K value, K1, she gets the first T. The first value of T was 3.66, 3.866 squared, then times the first value of W. The first value of W was 45.23. So I will check her values by calculating here. 3.8, sorry, this was 65. 3 point, no, not 65, it is 66. These are results for my students, so you can do the practical and obtain your results. These are just a guide. So 3.866 squared, 3.866 squared, then times 45.23. So my student gets her first K value as 876.0. Sorry, not 8, 676.0. That is her K value. Then first K value, second K value, T is 2.608 squared, then times W, which is 111.76. So this is 2.608 squared times 111.76. And my student gets 760, 760.2. So these are the K values she got here. So she writes here 676.0 and 760.2. The units were not necessary, so she did not include the units. Normally here they don't ask for the units, but the next part of the question that could always be here would be justify the number of significant figures you have given for your K values. So because T squared is to 4 significant figures and my W is to 4 significant figures, to maintain accuracy, the K values should be to 4 significant figures. That is normally a question here. In this particular practical, it is not there. But since T squared is to 4 significant figures and W is to 4 significant figures, to maintain accuracy, K values should be to at least 4 significant figures. When I say at least, it can be more, but not less than 4. So, okay, we shall see one practical which has such a question. Then explain whether your results support the suggested relationship. So if you are a teacher, you encourage your students to choose criterions or relations that they can always test. They choose limits they can always test. So for my students, some of them choose 5%, others choose 8%, others choose 10%, others choose 12%, others choose 15%. So a student can choose one of these as their limit. So like for my student here, she chose 15 and she said, let my percentage acceptance range. Acceptance, how do you spell acceptance? Let my percentage acceptance range of error in K values. Let my percentage acceptance range of error in K values be, and she chose 15%. So she was testing against 15%. So she got the percentage difference in K values. Percentage difference in K values equals to, so it is percentage difference, so you can get the highest 760.2 minus the lowest 676.0. So for her, she chose to divide by the highest. You can divide by the average if you want. So she chose to divide by the highest, which is 760.2, but I said you can divide by the average. That is 760.2 plus 676.0 divided by 2. So this should be times 100. And what does she get? When she presses her calculator, let me check if she pressed correctly. 760.2 minus 676.0 divided by 760.2 times 100. She gets 11.07 or 11%. So she gets 11%. And when she gets 11%, 11% is less than 15%. Now she writes a conclusion and she says, since my percentage since the percentage difference since percentage difference in K values is less than 15%, because she tested against 15, is less than 15%, K can be considered constant. K can be considered constant. So the relationship is supported. So the relationship is supported. So this is how my students present their work. So if she had chosen 10% and she calculates and she finds 11, so she would definitely say that since percentage difference in the K values is greater than 10%, if it is greater, then K cannot be considered constant. And if K cannot be considered constant, then the relationship is not supported. But in this case, since she chose 15%, then she would say percentage difference in K values is less than 15%. In this case, K can be considered constant, so the relationship is supported. If she had chosen 8% and she calculates and she gets 11%, still she would say since percentage difference in K values is greater than, remember she would have chosen 8%. So since percentage difference in K values is greater than 8%, K cannot be considered constant. The relationship is not supported. In this case, the relationship is supported. But if it was 8%, the relationship would not be supported. K would not be constant because the percentage difference in the K values would be greater than 8%. Okay, and the last part of the question is describe 4 sources of uncertainty or limitations of the procedure for this experiment. So this is always going to be the last question. Some of the sources of uncertainties, you will see them in the exam, in the practical. If you try to print and do the practical yourselves. But since we have calculated the 2K values, then we have a constant. We always have the first limitation as almost the same for every practical wherever we have 2 constants. So 2 readings are not enough. Because we took only we calculated 2K values, it is only because we had 2 sets of readings. So 2 readings are not enough. To draw a valid conclusion. So that is always mostly the same limitation for all questions where you calculate 2K values. How do we improve that? Take more readings and plot a graph. Take more readings and plot a graph. Take more readings and plot a graph. Number 2, or you could say take more readings, obtain more K values and compare them. You would say take more readings, obtain more K values, and compare. Okay, then number 2, I think my students also observed, if you do this practical, you'll also observe this, that the ruler was hitting the bench. So the rule hits the bench. The rule hits the bench. And there are several ways of reducing this. One way would be elevate the apparatus, that is raise the apparatus. Maybe you could put the cylinder on a small block. Elevate the apparatus. You could elevate the apparatus. You could clamp the cylinder if possible. You could project the end of the cylinder. You could project the end of the cylinder over the bench, so that when you put the ruler, if the end of the cylinder is over the bench, chances are high that when you put the ruler can be hanging in space rather than hitting the table. So you had to come up with a method of preventing the ruler from hitting the table. One of them could be projecting the end of the cylinder over the bench, so that it just extends. If this is the bench, you could project the end of the cylinder so that it continues slightly beyond the bench, so that when you put the ruler can be hanging in space, That is if you have a larger cylinder which has a large weight. So the ruler can be hung away from the bench so that it doesn't hit the bench. Then my student also said it was difficult to judge when one oscillation is complete. So difficult to judge when oscillation is complete. Difficult to judge when oscillation is complete, because when you displace the ruler, the second oscillation may not reach the same position as the first oscillation. So how would we solve that? So if it is difficult to judge when oscillation is complete, then it means we have to count oscillations from their center rather than from the extreme end. And if we count oscillations from the center, then we must put a mark at the center. So use a fiducial marker. Use a fiducial marker. You could also just put a pointer. Use a fiducial marker or pointer at the center. At the center of oscillation. Instead of counting, if the swings are like that, instead of counting from in position A, that it comes from A to B and back to A for one oscillation, then let the pointer be here, so that you count oscillations from this point here, from the center of the oscillations. Alternatively, you could use a video camera with a playback and a timer, or use a video camera with a playback and timer. Of course, if you record the experiment using a video camera that has a playback and a timer, you just view frame by frame so that you can easily see the number of the oscillations without any problem. Okay. And one other student also suggests that the oscillations were dying away quickly. When you perform this experiment in your lab, you will also see that the oscillations die away quickly. So you say oscillations die away quickly. Die away quickly. Or you would say there are too few oscillations. Too few oscillations. For some students, they couldn't count even 5 oscillations. Too few oscillations. Unfortunately, you could not be able to solve this, but you can give another method of improvement. For example, the 2 cylinders which I provided to my students, where they were made of different materials. And one student suggests that you could use a same surface. You could use the same surface or material for cylinders. So you notice that this improvement is not for this limitation here, but I know that this one affects the results. I didn't give the limitation correspond to that method of improvement. I didn't give the method of improvement for this one for oscillations dying away. So it means I'm still covered, whether I gave I can give a limitation without an improvement. I can give an improvement without writing a limitation. So all these are allowed. So this is how we go through this question. And I think if you print the question paper, you can try to, if you print the question paper and do the practical, you can just use these results as a reference point. So for the teacher, you can look for the confidential for this paper, May, June 2011, and print for your students. And then maybe you can use my video as just a guide. For a student, if you can be allowed to access apparatus in your laboratory, you can still print the question paper. And as you're doing the practical, you just refer to what I have recorded in this video. I hope it has been helpful. Thank you and bye bye.